Hello everyone, welcome back. So today we will be taking up three problems from the book Pathfinder, and this is from the chapter of NLM. So the three problems are mainly based on NLM and a little bit of circular motion. So this is problem number 1, and this is question 25 from the CYU section. So we have a stone that is tied to a cord. One has to move the free end of the cord on a circular path, pulling the stone on a larger circular path. Okay, so this is the end that is being pulled. Okay, and this is the end where the stone is attached. So in this way, a stone of mass m is whirled on a horizontal circular path of radius capital R with the help of a light inextensible cord of length L by moving the free end on a circular path of radius R with a uniform speed of v. Okay, so the magnitude of v is constant and they're both moving in horizontal circular paths. Tensile force in the cord becomes so large that the effect of gravity can be neglected. But at this speed, air resistance becomes considerable. So we have to find an expression for the force of air resistance. Okay. So acceleration due to gravity is going to be g. So let's try to understand what they mean by this line. Tensile force, when it is so large, the effect of gravity can be neglected. So what they mean by this is, okay, so let's try to draw the side view of the situation. So I'm just drawing a rough diagram. So this is, let's say, the horizontal circle in which the free end is being moved. Okay. And let's say this is the circular path of the stone. So let's take this radius as some R2 and this radius as some R1. Okay, so this situation that I drew is some arbitrary situation. Okay, so this is when mg is significant, right, in comparison to the tension. Okay, so now once we start increasing this velocity with which we spin this end, we can intuitively see that the rope will start climbing up, right? What they're essentially saying in the question is that there is some value of v for which it is almost in the same horizontal plane, right? So even though it can never be exactly horizontal, because if you just look at the FBD in this situation, mg will act vertically downwards, tension will be horizontal, and then there will be like air resistance force in the either out of the plane or into the plane, right? If you observe something here, mg will try to bring it down, right? So it can never be exactly horizontal, but it is very close to horizontal. Okay, so that's what they mean by this line. Basically, it is that the stone is moving in the same horizontal plane that the free end of the rope is moving. Okay, so that's basically how we have to model the situation. So now let's discuss the problem by drawing a good diagram. Okay, so this is the diagram of the given situation. So we have free end is moving in a circle whose radius is smaller, and the stone is moving in a circle whose radius is capital R. Okay, so I have not drawn the trajectory of the circle, but you guys get the idea, right? So now the main idea here is that these distances, if you observe, small r, L and capital R, these are all constants, right? So throughout the motion, so let's say when the stone will be somewhere over here, even in this situation, this distance will be capital R and small r is the radii of the smaller circle. L is the length of the rope. So these three lengths are always going to be constant, right? So what does that tell us? That tells us that this triangle, so let's name the triangle something. So I'm going to call it as OAB. So this triangle OAB will always be maintained. Okay, so after some time, what will happen is, okay, so basically after some time, when the ball B actually reaches this particular point, you guys can see this will be the new triangle OAB, right? Okay, so now if you consider these two triangles, what we can see is if this triangle OAB is like a rigid body which is rotating about this point O, right? Okay, and the reason we can treat it like that is because these lengths are fixed. So if you choose any 2 points on the body, so let's choose this point and this particular point over here. Let's say the distance between these 2 points is L dash. This distance is always going to be same throughout the motion, right? So we can consider this as a system of 3 rods that are interconnected and they are rotating about the point O. Okay, so the benefit of doing that is that now the point O is just the instantaneous center of rotation for the rigid body, right? So we know, so we can write the omega of the rigid body v divided by small r, right? Because we know the velocity of point A is v and the perpendicular distance from the axis of rotation is r. So I can write the omega as v divided by r. Or what we can do is the velocity of this ball, let's just take it as a variable u. Okay, now obviously it will be perpendicular to the radius because B is moving along a circle, right? So I can also write the omega. Now I also know the velocity of point B, it is u. So it will be u divided by capital R. So I can also write the omega as u divided by capital R. If you rearrange the terms, u will come out to be capital R divided by small r times v. Okay, so now let's try to draw the forces that act on the ball B. So the tensile force will be along the rope. So I'm going to mark it as T. Mg is into the plane, but we are going to neglect it because the question wanted us to neglect it. And then we have the air friction force, which is opposite to the velocity vector, which I'm going to name as F. So let's say I take this angle with the horizontal as theta. So we can say T cos theta, which is the force in the minus x direction. It will be equal to the mass of the stone times the horizontal acceleration. Okay, so now the horizontal acceleration is the centripetal acceleration, right? It will be u square divided by capital R. So we can say T cos theta equals mu square by capital R. Now guys, v is given to be a constant, right? Which means u will also be a constant. So this is basically steady state. So basically for steady state, we can say that the tangential acceleration should be 0. T sine component should balance out the friction. So we can say T sine theta is equal to our air friction. Okay, so now the thing is we need cos theta. So cos theta is pretty easy to figure out from this triangle by using cosine law, right? So cos of theta is going to be, the two adjacent sides are r and l. So this will become r squared plus l squared minus the opposite side squared divided by 2rl. Okay, so now once we know theta, what we can do is just divide these two equations. So we'll get tan theta. Now instead of writing tan theta, what I'm going to do is write it as sine by cos itself. And sine theta, I'm going to write as 1 minus cos squared, right? So this would become f divided by, I'm going to substitute the value of u as well. Okay, so now all you have to do is substitute the value of cos theta and you'll get the air friction as this particular value. You can also find the tension in the cord. All you have to do is substitute cos theta here. So yeah, that's about it for this question. Now let's move to the next one. Okay, so this is question 26 from the check section. And here we have a light inextensible cord whose, once again, which is wrapped around a frictionless cylinder of radius r that is fixed vertically on a floor that is lubricated with oil. Okay, so let's draw the floor first. Okay, so this is how the cylinder is fixed. So this is the floor and the cylinder is fixed on the floor, and it's given that the floor is actually lubricated with oil. Okay, now a bead of mass m is tied at one end of the cord and the other NP is free as shown in the figure. Okay, so the NP is over here and the bead is over here. Okay, the force of viscous drag on the bead due to the layer of the lubricating oil is proportional to the speed of the bead and proportionality constant K. Okay, so let's say hypothetically it is moving with velocity v. So on the floor, so we'll have to apply the fluid friction as K times v in the opposite direction. Now it's given if the free end of the cord is pulled at a constant speed of u along the cylinder, the bead eventually acquires a steady motion on a circular path. Okay, so a lot of words here. So firstly, the free end is pulled at a constant speed u. Okay, so this NP is being constantly pulled with the velocity of u and it's along the cylinder. Okay, so this P is pulled along the cylinder only. So after some time, the point P will be over here and it will be pulled like this only. So once again, the point P is always being pulled along the cylinder and the bead eventually acquires a steady motion on a circular path. Okay, so now the thing is, this bead wouldn't be along this cylinder. Okay, and I'll explain the reason in a bit. But they're saying eventually it will acquire a steady motion on a circular path, meaning after some time, when the velocities all become constant, what happens is the bead will be on some other circular path, okay, with some other radius. So they're asking what is the expression for the speed of the bead and the radius of its circular path when steady state is achieved. Okay, so that's the question. Okay, so let's draw a diagram and get into the analysis. Okay, so I'm saying this is my original cylinder. Okay, so before we draw a diagram, let's discuss why small m wouldn't move along the cylinder. Okay, so basically once we start pulling the NP, let's say in this particular instant, obviously this end will also move with the same speed of u. So now obviously guys, u is actually tangential to the path, right? So the mass will actually start moving in this direction. Okay, so now I'm going to draw the dotted trajectory. So let's say the mass reached somewhere over here. But now the issue is the string is something like this, right? So the tension will be pulling it in this direction, whereas the mass has a velocity in this direction. So now obviously, as you guys can see, it has no reason to move along the cylindrical track, right? It will, okay, it will move in some random trajectory, something like this. But they're saying finally it becomes a circular trajectory. Finally, it moves along a circular path. So let's just draw the final situation itself. Okay. Okay, so let's say this is the free end P. Okay, so this end is being pulled with the speed of u, right? Now, I didn't complete the diagram yet. So, okay, so the diagram will look something like this. Okay, basically the bead is somewhere over here, and this is how the strings look like. Once again, this end is being pulled with the speed of u. So what that means is the ball will also have a velocity of u in this direction along the string. Okay. Okay, so now the main point of discussion was that this ball is moving in a circular path, right? At the finally, when steady state is reached, the trajectory of the ball is a circular path. So let's name the radius as r dash. So it's the r dash that we have to find. Okay, guys. So one thing from basic circular motion, it's that the if we have a ball, if we have a particle that is moving in a circle. So let's draw the trajectory of this. So I drew a circle. So this will be the trajectory of the bead. So one simple rule from circular motion is that if a particle is moving in a circle, the resultant velocity must be along the tangent to the circle. If there is some component along the normal, it means that it won't be a stable circular motion, right? Its radius will change. So this component u that we earlier marked, this is only a component of the main velocity, which is v. Okay, so now let's try to find out some angles. So if I drop a perpendicular onto this line, this is r and this is r dash, right? So if I say this angle is alpha, and if I drop a normal to the black line, so this is alpha, this is 90 minus alpha, this will be alpha. So the component of v along the string is actually v sine alpha. So from the diagram, we can see the component of v along the string is v sine alpha, and this should be equal to u. Okay. So from here, we can directly figure out v. It will be u divided by sine of alpha. And sine of alpha is pretty easy. It is capital R divided by r dash. Okay, so this is equation number 1. So the tension force will be along the string once again, right? And the next force that we have to mark is force of friction due to the oil, and that will be opposite to the velocity vector, right? So this is how, so this is the direction of friction force F. So now I'm going to shrink the diagram a bit. Okay, so now we'll do force balance in the tangential and normal direction. So the equation, so F equal to ma equation in the normal direction. So T, so the component of T towards the center of curvature is T cos alpha, right? So we can say T cos alpha. This T cos alpha force provides the necessary centripetal acceleration to move in the outer circle. So this would be equal to m v squared divided by r dash, right? Why? Because v is the velocity of motion in the circle and r dash is its radius. And the t sine alpha component will be in the tangential direction. This needs to be balanced by the force of friction, right? So t sine alpha should be equal to f. Why should it be equal? Because it's steady state, right? Meaning the velocities are constant. So there shouldn't be any tangential acceleration, just like the previous problem. And the friction due to the oil, we can write it as k times the velocity of the ball, right? This was given to us in the question. So, okay, so now we can just divide this equation. So we get tan alpha as, and after substituting the value of v, we get it as kr divided by mu. Okay, so if I try to complete a triangle with this angle as alpha, so tan alpha is kr divided by mu, right? So we need sine alpha. So v comes out to be u divided by sine alpha, which is going to be square root of 1 plus mu divided by kr whole squared and the under root of this. Okay, so this is what we'll get for the value of v. And they also wanted us to find r prime. So that is just capital R divided by u times v. So we just have to multiply this with r by u. So this will become r times 1 plus mu by kr whole squared under root. Okay, so these are the two required answers for this question. Okay, so coming to the final problem. So this is question 28. So guys, before we solve this question, if you're still watching, do like and subscribe to the channel, and I'll be bringing more such videos in the future. Okay, so now let's move on to the question. So we have a small disk whose mass is m, and it is placed on a large horizontal floor which is lubricated with oil, similar to the last problem. Now here the force of viscous drag due to a layer of lubricating oil is given by this equation, the same equation as last time. And v is the velocity vector of the disk, and the value of k is given. If a force of constant magnitude f rotating with a constant angular velocity of omega is applied on the disk eventually acquires a steady motion on a circular path. Find speed of the disk in its steady motion. So once again, we have to talk about steady motion. So we have two informations given to us. One is that the disk moves in a circle, and second is that its speed will be constant. So in that case, we have to find the speed of the disk. Okay. So first let's talk about what they meant, what they're trying to say in this line, right? F has a constant magnitude and it is rotating with some angular velocity. So what they're trying to say is, so let's draw a circle whose radius has a length of, so I'm going to call this magnitude as f naught, okay, instead of f. So the radius of the circle is f naught, okay, representing the magnitude of this force. So they're saying that f naught rotates with an angular velocity of 0.3 radians per second. So basically f naught is a force that moves in this circle, right, with an angular velocity of omega naught. So let's say at t equal to 0, f naught points in this direction. Then at t equal to delta t, what will happen is this vector will rotate by omega naught delta t, and the force f naught will look something like this. Okay. So basically it's a phasor, right, which is rotating with an angular velocity of omega. Okay. So now let's keep this to the side and talk about our disk. Okay. Once again, it's given to us that it's moving in a circle. So let's say the radius of the path is capital R. Okay, and let's say the disk is present somewhere over here, and let's say its speed is actually v. Okay, so the viscous drag will be opposite to it, and its magnitude will be k times v. Okay, so the only other force in the horizontal plane is the force f naught, right? So now the question is, in which direction is it pointing? So okay, let's try to figure it out with the hints given. So firstly, we know v is a constant. So what that means is there cannot be no tangential acceleration. So there should be a component of f. So definitely a component of f should be in this direction. Okay, so let's call it as f parallel. So the f parallel should be equal to kv, right? So that the tangential acceleration becomes 0. And f perpendicular should obviously point towards the center of the circle, because this will be the force that is giving the centripetal acceleration. Okay, so let's place the f parallel vector over here. So with this, we can get a rough idea. So I'm going to just mark a rough arrow for the vector f. Okay. Now let's say this particular angle is some alpha, which f makes with f parallel. Or we can also say it's the angle that f makes with the tangent, right? Because f parallel is along the tangent. All right. Now another important idea is that the magnitude of f is constant, which is equal to f naught, right? Okay. So now observe something, guys. So when the disk moves around the circular path, we know that v is going to remain a constant, right? Which means the viscous friction, which means the friction is also constant. Now, if the friction is constant, then f parallel should also be a constant, right? Its magnitude should be equal to kv. What that means is f parallel, which is actually f naught cos alpha, should be a constant. Okay, and this should actually be equal to k times v. Now, if you compare these two equations, what that means is cos alpha should be a constant, or basically alpha shouldn't change. So the main idea that we had to guess in this question was that this angle alpha is a constant. Now, if the angle alpha is a constant, what that means is, okay, so I'm going to make a claim now. So that the claim is that for the angle alpha to be a constant, the omega of the line of this vector f parallel, right, this should be the same as the omega of the vector f naught. Okay, so what I'm saying is, so let's say f parallel is in the vertical direction and f naught vector is in this direction such that this angle is alpha, right? So we know after some time f parallel is going to rotate because the disk will move along the circular path, and in this point f parallel is in this direction. So if you compare, f parallel has rotated by some angle, right? So we know f parallel is going to rotate in the counterclockwise direction. Okay, which means the angle, this particular angle between these two vectors has decreased. Okay, but f naught is also going to rotate, right? F naught is also going to rotate in the counterclockwise sense because that's given to us. So that is going to increase this angle, which means if I want the angle between them to be a constant, okay, so let's draw that picture with the dotted line. So this is the final situation of f parallel, and this is the final situation of f naught. So f parallel rotated by this much, okay, and f naught rotated by this much. Now, if we still want the angle between them to be the same, there is only one way in which that is true. This angle, which f parallel rotated by, should be the same as this angle that f naught rotated by. Okay, so basically we want the increase in alpha to be equal to the decrease in alpha. So in extremely simple words, the omega of the vector f parallel should be the same as omega of the vector f naught. Now we know the rate at which f naught is rotating, right? That was given to us to be 0.3 radians per second. Okay, so from here we get omega f parallel equals 0.3. Okay, so now omega f parallel is just the omega of the circular motion, and that we can prove pretty easily. So at this point, let's say the velocity vector is something like this, and after some, and let's say it rotated by an angle of d theta. Now the tangent, and now the velocity vector is in this direction. So if I take the copy of the velocity vectors and if I join their tail, okay, so now I'm going to call this line as the normal line. Okay, so the normal line, we can see it rotated by an angle of d theta, which means the tangent will also rotate by the same angle. So this angle will also be d theta. Okay. Okay, so basically the rate of change of angle of the velocity vector is the same as the omega of the circular motion, which is d theta by dt. And the omega of the circular motion, we know it is equal to the velocity divided by the radius, right? So from here we get v equals 0.3 times capital R. So once again, the omega of f parallel, in short, it's just the tangential direction. So we want to figure out what is d theta by dt for the velocity vector or the tangential direction, and that is just the omega of the circular motion. Okay, so now for the second equation, so now for the next equation, we'll use f equal to ma in the normal direction. So in the normal direction, there's only one force, that is f naught sine alpha, provides the necessary centripetal acceleration, which is mv squared by capital R. So we'll eliminate the capital R from here, and we'll get f naught sine alpha as 0.3 mv. Now f naught cos alpha is just kv, right? So f naught cos alpha equals k times v. So now we'll just square and add these two terms because we don't care about sine alpha, right? So LHS would become f naught squared. RHS is kv squared plus 0.3 mv squared. Okay, so now it's just some simple algebra, and after that we get the velocity as 1.2 meters per second. Okay, so yeah, that was it for this video, guys. If you have any doubts, you can comment down below. And yeah, if you enjoyed the video, please do like, share, and subscribe. And that's it. Thanks for watching.